Okay, so we will be solving a problem perfect peak of array, where you're given an array A of size n and you need to check whether there exists an element which is strictly greater than all the elements on left of it and strictly smaller than all the elements on the right of it. If such element exists, we return 1, otherwise we return 0. We do not have to consider the corner elements, but they cannot be considered as the answer. Okay, so let's understand the problem using an example. Here you are given an array and you have to find an index I such that all the elements to the left of I are strictly smaller than the element at I, and all the elements which are right of it are strictly greater than the element at I. This is the task that we have to accomplish. So the first method that we will be using is the brute force or the naive approach of this problem. So in the naive approach, what we will be doing is we will simply traverse the array from the second element up until the second last element, and for each element we are traversing, we compare this element to all the elements to the left of it. Namely, for any element we are standing at, we compare it with the elements which are at the left of it. So we compare if all the elements to the left of it are strictly less than this element or not. If they are strictly less than the element, then yes, there may be possibility that this is the peak, perfect peak. So we so we traverse the right subarray and compare all the elements of the right subarray with the current element and check whether they are strictly greater than the element. If they are, then that means this is the perfect peak of the array and we return 1. If we do not find, then we move our pointer to the next position, to the next element, and repeat the process again. We compare it with all the elements to the left of it, and then we compare it with all the elements to the right of it. So we keep doing it for all the elements up until the second last element. If no such index is found, then we simply return 0. So that's the most naive approach. So what's the time complexity of this approach? Well, we are traversing n minus 2 elements, and for each element we are comparing it with all the other array elements. So that will multiply a factor of n. So this gives us a solution of big of n square, which is a quadratic time complexity. So for the given constraints of the problem, this complexity is not very good, so we have to optimize it. So how we can improve the solution? First of all, before thinking of the optimized solution, let's see the algorithm for this approach. Here is the brute force algorithm. This is called the brute force algorithm. Select each element from the index first to n minus 2. Check if all elements to the left of it are strictly less than it. Check if all elements to the right of it are strictly greater than it. If both of the above conditions are satisfied, then we return 1, otherwise we return 0. So that's the pseudocode for this approach, and let's now how we can improve the solution, how we can improve the complexity of the algorithm. This is a quadratic complexity, we have to bring it down. So the first observation that we do is that for any element that we are traversing, what we are doing is we are comparing all the elements to the left of it. So we have to do n number of comparisons in the worst case. So how we can improve here? We can think of it in this way, that rather than comparing all the elements to the left of the element ai, we can simply keep track of the largest element up to I. So if the largest element up to I, namely in the range from a of 0 to a of 1, a of I, so in this range inclusive, if the largest element is, let's say, prefix max, if this largest element is greater than the element ai, that means there exists an element before I which is greater than that. That means this is not a valid index. So for I to be a valid index, the prefix max must be equal to ai, because then only we can make sure that all the elements before I, namely from 0 to I minus 1, are strictly less than ai. Similarly, for the right subarray, we have to pre-process, we have to know what is the suffix, what is the minimum element in this portion. So in the range a of I to a of n minus 1, we need to know what is the minimum element. If the minimum element in this range is less than the element at I, that means there exists an element in the right array which is less than ai. So in that case this is not a valid perfect peak. So for a valid perfect peak, this element, which is the smallest element in this range, must be equal to ai, because then only we can make sure that from the range I plus 1 up to n minus 1, there is no element which is less than ai. So let's call this suffix min. So for a valid perfect peak, uh, this ai and this prefix max and this suffix min, they must be equal, because in that case what we are saying, that prefix max is the maximum element in this range which is same as ai. So from the range 0 to I minus 1, there is no element which is greater than ai. Okay, so if there is no duplicate of ai, we are considering that there is no duplicate of ai which exists in the left subarray in this range. Similarly, we are assuming that there is no duplicate of element ai which exists in this range. So in that case we make sure that this suffix min is equal to ai. If this condition is satisfied, then that means this is a valid perfect peak, so we return 0 in this case. Now the next task is to think that how we keep track of prefix max and suffix min, because we have to check for each index I what is the prefix max for that index, what is the suffix min for that index, and the element at that index. So for that we can pre-process two arrays, prefix max and suffix max, such that prefix max I is the smallest, it is the smallest, uh, it's the it's the largest element from 0 to I inclusive. Similarly, suffix min I is the smallest element from I up to n minus 1. So once we pre-process these two arrays, we have something like this. So for the given array A, we have prefix max array pre-processed like this and a suffix min array pre-processed like this. So once we have these arrays, it is very easy that we compare with once we have this type of configuration, we have prefix max array, we have suffix min array. Now we start iterating from the second element up until the second last element of the given array, and if we find that at some point ai is equal to prefix max I, if we find that ai is equal to the prefix max I and ai is also equal to the suffix min I, so at that index we're gonna check, let's iterate over the array. So for the first element it's not equal, for the second element it's not matching, for the third element it's not matching, for the fourth element it's matching with prefix max, and this is also matching with the suffix min. So at this index all the three values are matching. That means the, that simply means that the elements to the left of it must be smaller than this element if there is no duplicate of 6 which exists before it. Similarly, there is no value which is smaller than 6 after this index up until the last index. That means this is the index such that there is no element to the left of it which is strictly smaller than which is greater than it. So all the elements to the left of it are strictly smaller than this, and all the elements to the right of it are strictly larger than this. So we return 1 from here. Okay, so that's the idea, that's how we solve this problem. Here we have to take care of another condition such that suppose there exists a duplicate. Okay, there exists a duplicate. So if there exists a duplicate, namely the case if there is a duplicate, then that means uh, the prefix max I minus 1 is also equal to the is also equal to the ai, and in that case in that case the condition is violated because there exists an element before the index I in the array A which is not strictly smaller than the element ai. So we do not consider that element and we keep traversing the array in the forward direction. Also, if there is a duplicate element after the index I, then suffix I plus 1 is same as suffix I. So in that case Also there exists an element after the index I such that the element at ai is not strictly less than the element 8 at some index which exists after ai. So in that case also the condition of perfect peak is violated, so we return so we keep traversing the array and we do not consider such elements. So up until the second last element, after the traversal is over, if we do not find any element, any perfect peak in the array, then we return 0. Okay, so that's the idea. So what's the complexity of this approach? So we are pre-processing two extra arrays, which is prefix max and suffix min. So for pre-processing the array prefix max, it takes O of n plus O of n for pre-processing suffix min plus O of n for linearly traversing the array ai. So basically it gives us a complexity of O of 3n. So which is linear time complexity, which is much better than the previous approach which was quadratic. So we have, so this is the optimal solution to the given problem. And let's see the algorithm. Here is the approach which gives us the optimal solution. So in the case of duplicate elements, namely if the element here which is here is also the element at some previous position, then that means we have to, that means the prefix I minus 1 is same as the element ai. So in that case all we have to do is that we have to skip that element, because that does not satisfy the perfect peak of array property. So let's see the implementation part. Okay, so here's the function perfect peak, where a function where a vector is passed, where vector a is passed, n is the size of the vector. We declare two arrays, prefix max and suffix min, and we initialize the prefix max with the first element of the array and suffix min with the last element of the array, and we pre-process the two arrays, and once we pre-process them we iterate over the given array and check if there exists a peak element. So how we check that? We check if some element in the array is same as the prefix max, the element which is in the prefix max. That means this is the basically all the elements, basically this is the maximum element up to the index I. And if this element is same as the suffix min as well, that means this is the smallest element up to the index I in the array A. So if that's the case, we have to check if there is some duplicate or not. So if there is a duplicate in the array A, then the prefix max I minus 1 will be same as ai, and suffix I if there is a duplicate in the right part of the array, then suffix min I plus 1 will be same as ai plus 1. So if there is no duplicate, that means this is the given perfect peak and we return 1. So after the iteration is over up to the second last element, if we do not find any perfect peak, we return 0. So this is the implementation of the given algorithm. So that's all. Let's submit the solution. Okay, test case is passed. So that's how we solve this problem. It was an easy problem. It was asked by Flipkart. You can see Flipkart is the tag. Hope you enjoyed the problem. Thank you very much.